Welcome back, students. Let's resume our discussion. In the previous video, we defined partition. Wrong section, excuse me. We defined partition and then we defined Riemann sum. Let's review this concept. Partition. Given closed and bounded interval a to b, we define a partition like this. Start from the starting point a, we call it x0, and then x1, x2, x3 all increasing order and end at xn, which is equal to b. Now here's a visualization starting from x0 equal to a, ending at xn equal to b, and we have a bunch of points in the middle. And we define delta xi as xi minus 1. Basically, it's the width of each subinterval. x1 minus x0, this is width. And then the next width, delta x2, this width, the biggest among these, and then this width, and so on. And then we say delta x, without the index, is the maximum of all those widths. In this particular case, the red one, delta x3, is the maximum. Why is this so important, delta x? Because if the maximum go down to 0, then all delta xi's will have to go down to 0 as well. Now let's define Riemann sums. We define Riemann sum like this. Delta xi's, those are given by partition, and then yi stars, they're selected arbitrarily between the minimum and the maximum in that interval. Here is a visualization, and this program is randomized, so you can run over and over again. You're going to get different yi value each time you run, but the partition is fixed, so x coordinate will stay the same. Delta xi is the width of the partition, so we have width of this rectangle, and yi star, that's the height, y coordinate value, so height of the rectangle. So height times width, this quantity is each individual rectangle, and then add them all up. What do we have? We have sum of those areas of the rectangles. And as you can see, the sum approximates the signed area underneath graph. Not very well, because we have only 4 rectangles here. But if we have 4,000 rectangles with very, very thin delta xi close to 0, then you're going to get much better approximation. But in any case, this is the definition of the Riemann sum. Now, even though I showed you the picture, this definition does not depend upon the picture. They stand alone algebraically, and the picture was just there to help you. It is very different from this kind of description, where it was directly coming from the picture. Without the picture, this expression does not make any sense. This one, even without the picture, this is perfectly good definition. The picture is just there to help you understand. Okay, so much for the partition and Riemann sum. Now let's go over to Riemann integral and let's define it precisely. And here you go. This is the definition of the definite integral, or Riemann integral, named after this gentleman, Georg Friedrich Bernhard Riemann. Sorry about my German pronunciation, I'm not good at it. Now this definition is valid only when the limit exists. And for example, how did he define the derivative, by the way? Does everybody recall? F prime of a is equals to limit h is going to 0, f of a plus h minus f of a over h. That was the definition of the derivative. This is the difference of y coordinate. This is the difference of x coordinate. So this is basically rise over run. And the limit, if it exists, is the derivative. Turned out it is the slope of the tangent line, and so on and so forth. But in any case, this makes sense only when the limit exists. Likewise, this definition of the definite integral makes sense only when the limit exists. However, unlike this derivative case, this limit is much more difficult to handle because this is really diverse quantity. You see, how many partitions are there? They are really diverse partitions, uncountably many. Given interval, I could put hundreds of thousands of points all in haphazard fashion, and then we have to consider them all. So this is really diverse quantity. Now for each partition, we have a lot of randomness as well, because yi stars can be anything between the minimum and maximum. So we are talking about really diverse quantity, and they all point toward the same limit. This is very strong condition, but if it does, we're going to call that common quantity as a definite integral or Riemann integral. In any case, this is difficult limit to handle, but it's precise definition anyway. So what we can say is we define the definite integral precisely and successfully here. If the limit exists, we say the function is Riemann integrable in this interval a to b, and so on and so forth. And we can do some computation when f of x is a continuous function. You see, the fundamental theorem of calculus, where is it? Goes like this. We need a continuous function. If it is continuous, then the integral exists and the value is the net change of the antiderivative function, and so on and so forth. What do you mean by the integral exists? That means this limit is valid. So for continuous function, it works out okay. We're not going to prove that one, however. The proof of the fundamental theorem of the calculus is way beyond calculus 1 and 2 level. And we're going to do that probably in real analysis 2, I think. Maybe real 1, but I think it's better at real analysis 2. Okay. Do we have time to do some applications of this definition? Probably not, so let's have some fun going through some visualizations, and then we're going to do some application in the next video. Here's a visualization of an arbitrary Riemann sum. Let's see, we have 50 points in there. It's 50 rectangles here. And the approximation, pretty bad. We have a lot of really thick rectangles here, which represent pretty bad approximation. As you can see, the deviation is pretty large. This is really randomized, so if I run it again, I'm going to get very different approximation. And then it depends upon what we get, but wow, this approximation is really bad. Sometimes I get lucky and then get pretty good approximation, but this is really randomized, so there's no telling what I'm gonna get. Wow, 1.49 something. This is really bad approximation. But then again, the point is made. Why am I doing this? In order to capture the worst possible situation for proper definition. Now let's improve our approximation. Now that our definition is done, let's consider a little bit better approximation by removing some randomness. Here, same 50 rectangles here, but the same width. So the approximation is much better than before. And not much randomness here. There is some, but not much. The width will stay the same. All the height of those individual rectangles will change. So if I run it again, you see some change, but not a whole lot, both for pictures and also for the numbers. Now let's remove even more. Let's go over to midpoint approximation. In this case, no randomness whatsoever. Instead of taking arbitrary y value, we simply take midpoint and then take that function value here. So each rectangle hits the curve at the midpoint, top of the midpoint. So if I run it again, no change. Now let's improve the approximation. Let's go to 50 rectangles as before. As you can see, pretty good approximation. Not a coincidence, because we're trying to improve approximation by taking the midpoint. Let's go back to 10. Now let's consider another kind of approximation, left-hand side approximation and also right-hand side approximation. This is a left-hand side approximation. As you can see, the curve hits the left-hand side corner point, the left-hand side endpoint of each subinterval. Here is right-hand side approximation. Right-hand side corner point hits the curve. Left-hand side corner points versus right-hand side corner points. Both of them put together. Left-hand side, right-hand side. Oh, by the way, this is midpoint, hitting the midpoint, as you can see. None of those have any randomness here. However, in terms of approximation, the midpoint approximation is the best. Nonetheless, everything goes to the same limit, so you can use these to calculate the limit of certain Riemann sum using the fundamental theorem of calculus. We'll come back and discuss in the next video.